All right, so let's talk about enzymes. So here I have a reaction. This is sugar, all right? So when I oxidize sugar, carbon dioxide is given as a result, and this is the delta G for the reaction. So my first question for you is, which of the following is true regarding the reaction above? So given this information with this reaction, what would be true? Well, we can see right away that the delta G is negative. So what does that mean? Well, a negative delta G, as we know now, means it's spontaneous, means it gives off energy. And we know that because sugar has calories in it. When you digest sugar, you're getting energy from that, right? And it's actually quite a bit of energy. A mole of sugar, minus 686 kilocalories per mole. But let's think about the rest of this. So one thing I want you to understand is that spontaneous does not mean instantaneous, right? Spontaneous means it's energetically favorable. So here I have a packet of sugar, right? I know there's a lot of energy in these packets of sugar. And so does that mean I'm really brave holding these sugar? I'm even tossing it around. These are like little bombs, tons of energy in these. And yet I'm not worried about them exploding on me, right? It's because even though the digestion of this sugar can give off a lot of energy, it doesn't mean it's going to be instantaneous. All right, so let's think about why for a second. So again, glucose oxidation, highly spontaneous, but it can be left out without any loss. So let's also think about this for trees. We know that trees have a lot of energy in them, right? Forest fires create a lot of heat, but yet you're not too worried, hopefully, by sitting underneath a tree in the shade. You're not worried about it spontaneously combusting. Again, this is because even though it's favorable for that tree to burn and give off energy, it's not instantaneous. It needs a spark, right? So usually a forest fire is caused by someone being careless with a fire in the forest, or throwing a cigarette butt out, or maybe a lightning strike. But either way, something has started, has given the energy needed to start it. And that energy required to start the process is called the energy of activation, right? So this is the idea here. So on the y-axis, we have our amount of energy, right? And this is the progression of the reaction. So as it starts with the reactants and progresses to the products. And so first of all, is this reaction as shown here, would that be exergonic or endergonic? Well, this would be an exergonic reaction. The reactants have more energy than the products. That means overall, as we move from reactants to products, we give off energy. So this would be like the sugar with its negative delta G of minus 686. That's an exergonic reaction from here to here. However, we do have this energy of activation. So this energy of activation is this hill of additional energy that's needed to get over the hump to go from reactants to products. Now, this does not change the delta G. The delta G, the change in energy from reactants to products, is this right here, right? Delta G is the energy of the products minus the energy of reactants, is the change there. The energy of activation is the extra energy we need to get over the hump, but it's given back. So that doesn't affect the delta G. Any energy we add to get over this is going to be given back, right? So the energy of activation is not part of the delta G, but this is why reactants don't automatically instantaneously go to products. So even though my sugar packets will give off energy when I break that sugar bond, there's enough of this energy barrier that it's not going to happen automatically. It needs something to help catalyze it, something to speed it up, or something to get it started. Just like the tree is not going to spontaneously combust, even though once it starts, it can give off a lot of energy. It's exergonic. It needs something to get it over its energy of activation, a lightning strike, a spark, something like that. Right? So those intermediates on the way from the reactants to products, they might have a higher energy level. This is where bonds are stretched or things that are kind of having to be brought together. That can take a little bit of energy. And so all of this has a little bit of an energy hump that it has to get over. Right? And that's the energy of activation, the boost of energy needed to get the molecules past that transition state. So that transition state is the high energy intermediate state. So the energy of activation is the amount of energy needed to get over that. So if we take this back to our sucrose, right? Sucrose, if you'll remember, that's my table sugar here, it's actually glucose bound to fructose. And here's our glycosidic bond holding one sugar to the next. And breaking that bond gives off energy. That's the first step in digesting and getting calories from sugar, right? So this here would be our reactants, that sucrose with its glucose bound to fructose. Now, to break that glycosidic bond, we know it's a hydrolysis reaction. That hydrolysis reaction means water needs to get in here and basically break this bond. But in the process, water being there very close to this while the bond is not yet broken, that's a high energy intermediate. It takes a lot of energy to kind of force this to happen. And then once it does, the breaking of that bond gives off a lot of energy. And so our products, where glucose is separate from the fructose, that's down here. It has less energy. Breaking the bond gave off energy, right? So we started with the bond intact. The difference in energy for that intact bond versus the broken bond is this right here. That's our delta G. But because it takes a little bit of energy to break that, there's that hump. And so what that means is, even though digesting this sugar is going to give off a lot of energy, that's not going to happen spontaneously. This hump is too hard to get over. So what this means is, we know that an exergonic reaction is like rolling a big boulder down the hill. If you roll the boulder down the hill, it gives off a lot of energy. If you're rolling it up the hill, it takes energy, right? Downhill is exergonic, uphill is endergonic. Downhill gives energy, uphill takes energy. But if I have that boulder here, I still am going to need to put in a lot of energy to try and get it over this hump. And as soon as I do, it'll go off by itself. But there still has to be energy put in to get over the hump. That's the energy of activation. And so let's go back to this for a second. So let's answer this again. Which of the following is true regarding the reaction above? Well, we know it will be spontaneous because it's a negative delta G, but we also know it will not take place immediately because we have that high energy of activation. All right. B is incorrect because the free energy of the products is actually lower than the reactants. That's how we know the delta G is negative, right? The reaction will give off energy, and it might not happen automatically because we have that energy of activation that it has to get over, right? The change in free energy being negative, that actually means it's spontaneous, which will help it happen. I actually don't need to put in a net input of energy. I just have to get over that energy of activation, which is why C is the answer. The reaction gives off energy, it's exergonic, but it has that hump, that energy of activation that it has to get over, right? And this answer is why a lot of things, even though they're exergonic, they're not going to happen spontaneously because you need help to get over that energy of activation. The lightning that sparks the forest fire, or enzymes in my digestive system that help start that bond being broken. All right, so let's think a little bit more about enzymes. Which property is a false statement about enzymes? All right, we're going to come back to this again later and see if we can answer it again then. So let's talk about properties of enzymes. Enzymes are usually protein, but they can be RNA. So we've been learning more and more recently that RNA has some enzymatic activities, but usually enzymes are a single protein or a complex of proteins that come together. That would be the quaternary structure if multiple proteins come together to be an enzyme, right? And what enzymes do, and this is probably the most important part, they speed up a chemical reaction by lowering the energy of activation, right? So that hump of energy that's needed to get over, they help lower that so that the reaction can happen a little bit more easily, thus speeding up, right? So let's think about this for a second. So what I want you to do is get out a piece of paper, all right, and start with this. So this is our energy diagram, and this is the course of the reaction. This is kind of what we were looking at before. I want you to label the energy of the reactants, label the energy of the products, label the delta G, and the energy of activation. Make sure you can start to recognize these things. Right, so seriously, go ahead, pause, stop, put this on a piece of paper like we were doing this in class, and go ahead and do that. All right, so let's take a look at what you were able to do. So this right here would be the energy of the reactants, right? Reactants are how they're starting, products is how they're making or ending, and so this is the energy level, so that's the energy of my reactants. That right here is the energy of my products. Not at the bottom, but right here where that kind of my reaction line ends. That then is my delta G. The delta G is always the difference in energy from the products to the reactants, right? And would this be endergonic or exergonic? Well, this would be exergonic because we can see that the products have less energy than the reactants. So if you take less energy minus more energy, that becomes a negative delta G. Another way to think about it is this is a downhill reaction, right? So it's giving off energy, that's exergonic. So my delta G here would be negative, but that's the delta G. It's always the difference between the reactants and the products. The delta G does not include this transition state. It's just where were we at the beginning to the end. Then that would be my energy of activation. That's the energy hump I have to get over in order to get from reactants and then on to the products. All right, so one of the things that we know is that all molecules have energy. And if you look at the number of molecules, there's this bell-shaped curve of energy. So some molecules just naturally have higher energy than others, and so forth, and it looks like a bell-shaped curve. And so let's say there's a certain amount of energy that's needed to get over this hump, right? So if this hump is at a certain amount of energy, a molecule would need that much energy to get over. Right? And so if a reaction is at, or molecules are at 25 degrees Celsius, this would be its energy level here. And let's say this line right here, that's the amount of energy needed for the reaction to occur. So in this, very few molecules will have enough energy to make that reaction occur. Now, if we were in chemistry and I needed that reaction to occur more quickly, what I would do is put it on a Bunsen burner. I'd heat up the reaction. And when you heat up the reaction, you're giving the molecules more energy. So now that bell-shaped curve of energy is shifting over. So at 75 degrees, that energy curve kind of looks like this. And if this is still my line for the amount of energy needed, I have more molecules that are going to have that much energy. So I've sped up the reaction. It doesn't mean it's going immediately, but I have more molecules that have enough energy. Right? But we can't do that in biology. We can't heat up our cells to speed up the reaction. So another option is to lower the bar. So in the heating up the reaction, I moved my energies. I gave my molecules more energy. But if I can make that energy of activation lower, I can make the energy needed to get over it lower. And in doing so, even without heating up the reaction, now more molecules have enough energy to get over. That's the whole idea behind catalysis and enzymes. They lower the energy of activation, allowing more molecules to have enough energy naturally to get over that energy hump. Right? And so here's how I like to think about it. I call these my suicidal high jumpers. Suicidal because there's no mat down here. But anyway, they're over here. These high jumpers have to jump over this bar to get here. So this represents the reactants. This represents the products. This represents that transition state, so the energy of activation they have to get over. Right? So there's only so many of these that are talented enough to high jump over the bar. Very few. What I could do is give them more energy, soup them up, make them jump a little bit higher. But we know we can't do that in our cells. We can't heat up things. So the other option is just to lower the bar. All right, so if I lower the bar, I'm lowering the energy of activation. Now with the same amount of energy they had before, more are able to make it over. That's speeding up the reaction. That's catalyzing it. And that's what an enzyme does. Enzymes lower the energy of activation so that the reaction can happen more quickly. Now notice that what didn't happen is the energy of my reactants and the products didn't change. So my delta G did not change. All I did is sped it up by lowering the energy of activation so that there's more likelihood of the reaction being able to occur.